we actually discussed in the last class. So to quickly go through the things that we discussed in the last class was the arithmetic instructions. Okay, so we talked about arithmetic instruction. Okay, so in arithmetic instruction, we mainly concentrate upon the unsigned numbers. Okay, but actually it is not the case. We also need to consider the signed numbers. Okay, now the concept of signed and unsigned number, what actually it is. So this concept is basically for the programmer. So it is not a concept which is generally being used by the microprocessor or a microcontroller, because microprocessor and microcontroller merely understand the sign of zeros and ones. They don't understand whether the number is signed number or whether the number is an unsigned number. Means the add instruction, yeah, it can be used for the signed number as well as it can be used for the unsigned numbers. Okay, but we need to take a special care about when we are dealing with the signed numbers. Okay, now where we can have the requirement of the signed numbers. Okay, suppose if we are talking about a temperature. Okay, so the temperature can be range from -50 degree to +50 degree. So at that time you need to mandatorily take the consideration of the sign. Okay, otherwise there are some of the other data where the sign and unsigned is not very important. But yes, in some of the cases the sign is very important. Okay, so how we can deal up with this kind of situation in a microcontroller? Okay, so that can be done with the help of a concept of a signed number. So today we are going to discuss the concept of the signed number. So the arithmetic operation, yeah, they basically remain same as we perform the arithmetic operations over the unsigned number, but we need to take special care about the things. Okay, so in today's class we will be talking about that what are the special things that you need to take care about when we are dealing up with the signed number. Okay, so today we will be discussing the concept of N flag, S flag and V flag. So all these three flag will help us to understand the concept of the arithmetic operation of the signed numbers. Okay, already we discussed that C flag, carry flag, that was generally being referred when we are doing the unsigned number arithmetic. But if we are talking about a signed number arithmetic, then from microcontroller point of view there is no difference, but from a programmer point of view we need to take a special care about the flags, because we need to see the flag for whether the results are correct or incorrect results. So in today's class we will be discussing the concept of the signed numbers, and in concern to that we will also be discussing about the different flag associated with when we are discussing about the signed numbers. Okay, and at an end we will be also discussing about some of the another instructions that are what we call it as a logical instruction and the compare instructions that are available in our AVR microcontroller. So let's get started discussing about the side number concept and the arithmetic operation as well as some of the logical operations also. Okay, so I'll be trying to share my screen with you, so please let me know whether my screen is visible to you or not. Okay, so sign number concept and the arithmetic operation. Okay, so as already I have told you that the arithmetic operation, yeah, it would be carried the same way we used to carry out microcontroller would be carrying out the same arithmetic operation the way it used to do for the signed numbers, but as a programmer we need to take care about the results. Okay, so the concept of signed numbers in the computer we'll shortly go through the things that what is the concept of the sign numbers in the computer system, or basically we can't call it as a hardware system. Okay, so in everyday life the numbers are used that could be positive or negative. For an example, a temperature of 5 degree below can be represented as -5 degree, and 20 degree above can be represented as +20 degree. Okay, so the computer must be able to accommodate such numbers. Okay, the computers, yeah, suppose if I want to make a log of a temperature of the whole day, okay, it may be ranging from -25 degree to +25 degree, and if I want to maintain the log of it, then definitely this kind of numbers should be handled by our computer system. Okay, because we are not going to take the reading every time. Yeah, we would be designing a system which will be frequently daily taking the reading, and it will be storing the number in the database. So to do that particular thing, the the inventors of the computer have decided the following arrangement for representing the sign positive and negative number. Okay, so what they have decided is the most significant bit, MSB. Already we have discussed this thing when we were discussing about the sign number in our 8085, that the MSB, or we can say that the D7 bit is kept aside for the sign, for the plus or minus. Okay, while the bit is reset, while the other bits that are left, means d6 to d0 to d6, okay, they are kept aside for the magnitude purpose. Okay, the sign is represented by 0 for positive and the number and 1 for the negative number. So already we have discussed this thing in the previous case when we were talking about the 8085. Okay, so in sign bit operand, d7 bit, yeah, it is for the sign, and rest of d0 to d6 they are set aside for the magnitude of the number. Okay, suppose if I'll say that my d7 bit is equals to 0, the operand is positive, and if d7 bit is equals to 1, the operand is negative. And yes, we already discussed this thing when we were discussing the status register, that d7 bit is nothing but it is an end flag of our status register. So whatever the value you are having in your d7, it is being reflected in your end flag. So you don't have to check it what the d7 bit is, you can directly check about your end flag. Okay, so what are the positive number? So the range of positive number that can be represented by this format is from 0 to plus 127, because we got only 255 combination, and out of this 255 combination we need to kept aside 128 combinations for negative numbers. Okay, so if this is the format we can we are having, okay, then we can store a number which is a positive number from 0 to 127 plus. Okay, so if the magnitude of a number is larger than 127 number, then 16-bit operands must be used. So you, if the number is greater than 2 to 127, okay, plus 127, then rather than using only 1 byte, then you need to use a 16 bits of an operand for that particular thing. Negative numbers, so for the negative numbers, d7 bit is equals to 1. So if d7 bit is equals to 1, then the number is represented as a negative number. Okay, however the magnitude is represented in the 2's complement. So this is the thing that you need to keep in mind, that always the magnitude is represented by 2's complement. The reason is, we already discussed this reason when we were talking about 2's complement and 1's complement in your digital system design. Suppose if I talk about 1's complement, then there can be two zeros in the 1's complement system. So generally computer systems adopt the 2's complement for the negative number. So every negative number, they are represented in the 2's complement. Okay, if you go for the 1's complement, then 0 0 0 0 is also 0, and 1 1 1 1 is also 0. So that is the reason we generally go for the 2's complement method, where we can only, so I think this is the point of difference that would have been talked in your digital system design subject, that what is point of difference between 1's complements and 2's complement. Okay, so that is why majority of the computer system adapt this 2 complement system for the negative number. Okay, so suppose the d7 bit is equals to 1, the rest of the bits, that would be the 2's complement of the magnitude of whatever the number that is being represented by that negative number. Okay, now there is a very important thing that is happening, or I can say that there is a very big problem that is occurring in when we are talking about a signed number, that is an overflow problem. Okay, so first of all we need to discuss what is an overflow problem. So already we have talked about that your d7 bit is not a part of your magnitude. Okay, so the magnitude is only from d0 to d6. So whenever you are going to perform an addition operation, then there may be the case that the carry may be generated from d6 to d7. Okay, and if this is a carry generated, yeah, there would be a problem, because it is going to alter your sign. Okay, because d7 is for sign, and if the carry is propagated into the d7 value, then the sign bit is supposed to be get altered. Okay, so this problem we called it as an overflow problem in the sign number operation. Okay, so let us discuss that thing in a detail. So now when we are using a sign number, the serious problem sometime arises, that is that we must have to deal up with, and this problem is what called as an overflow problem. Already I have discussed that whenever the carry is being propagated from d6 to d7 bit, okay, it is going to alter your sign bit, and we don't want the sign bit to get altered. So that is the reason, yeah, there is an overflow problem. So we need to deal up this overflow problem. So in case of our AVR, this condition indicates the existence of error by raising the V flag. That is what we called it as an overflow flag. Already we have discussed this flag when we have discussed the status register, that when a carry is generated from D6 to B7, then overflow flag is supposed to be raised. Okay, so whenever the overflow problem is occurring in an AVR while you are doing an arithmetic operation over the signed number, then the V flag must be checked every time, because V flag would be giving you that whether the overflow has occurred or not. Okay, and if the overflow has occurred, you need to get the things corrected by yourself. Okay, so so yes, it is a task of your AVR microcontroller to indicate that yes, there is an overflow occur, but who is going to take care about it? There's a programmer. So the programmer needs to take care about this overflow problem. Okay. Now the CPU only understands the values of ones and zero. It don't understand anything else. Okay, and ignores the human convention of positive and negative number. It does not going to deal up with what the humans are going to interpret. Okay, it's only understand the zeros and ones. So yeah, it is going to tell you that error is occurred, but that is with help of a V flag, and it is a task of mandatory task of a programmer to take care about this overflow problem. Okay, so what is overflow? Already we have discussed about it. So if the result of an operand on the signed number is too large for the register, an overflow has occurred and the program must be notified. Okay, so that is, if I'll say that I'm doing an addition of two signed bit numbers. Okay, and if the resultant number, means if the addition of or the sum of these two operands are greater than that, it can be accommodated in the 6 bit, then there would be a case of an, or there would be a problem of an overflow. That is nothing but, in simple word, we can say that if a carry is propagated from D6 to D7, that is the problem of an overflow. So this is being explained over here with an help of an example. Let's say that LDIR 20 0 cross 60. Okay, so 0 cross 60. Okay, you can see over here I have considered it as a 0 cross 60, but actually what I'm interpreting it over here, it is hexadecimal 60, but it is actually being implemented as, or it is being represented, or it is interpreted as plus a 70, because 110000, it's nothing but it is plus 70. Same way it is earlier R21, then 0 cross 46. So 0 cross 46 is nothing but is 1000110. Actually, if you convert this number into a binary number, then this number is equals to 96. Okay, now when you add up these two numbers, so whenever you add these two numbers, okay, adding this, you will find it out that 1 plus 1, that is equals to 0 with carry 1. So the carry is being propagated from D6 to D7 bit. Okay, and the result is 1 0 1 double 0 double 1 0. Okay, so actually if you consider this bit as a sign bit, so this sign is nothing but it is equals to negative number. Okay, so actually it is being interpreted as minus 90, but the exact value that you must be getting is 166. So it will not be giving you 166. Okay, so it will be giving you this number. Okay, and this number is exactly equals to minus 90 as per our interpretation. Okay, so you will not be getting a valid result. Okay, so over here if you seek about the result into your R20 will be showing you A6, because this is 8 plus 8 plus 2 10, that is A, and this is 6. So A6 would be the result that you would be available in your R20, but actually you want the result that is equals to minus 9. If you go for the human interpretation of what you, a programmer, is interpreting, is if these two numbers are sorry, this bit is equals to 0, the rest of the bits is the 2's complement. So if you take the 2's complement of this number, which is 1 0 1 1 0 1 0, okay, so then this is exactly equals to minus 90. Okay, so that is an error. So this would be intimated to a programmer with the help of the raising of your V flag. Okay, so according to the CPU, the result is negative, that n is equals to 1. Again, you can see that n is a negative value. So n is equals to 1, which is wrong. It is not actually the negative number, but it is 166. So there is an error. Okay, so the CPU states that V is equals to 1 to indicate the overflow has occurred. Okay, so we need to check about the V flag. So after that we need to check about the V flag. If V flag is equals to 1, then we need to take a correcting action. Okay, so CPU sets the V flag to indicate the overflow error, but it is that N flag which is a D7 bit. Okay, so if N is equals to 0, sum is positive, and if N equals to 1, the sum is negative. That is direct interpretation that we have already considered while we are considering the sign numbers. Okay, so this thing can be intimated with help of your V flag. Okay, so this is the same thing that I have discussed, that in a given example plus 96 was added with plus 70 and the result according to the CPU is minus 90. The reason is there is an overflow. So the reason that the result was larger than the R0 code contained, okay, uh, like the other 8-bit registers, so R code contained value which is more than or less than equals to plus 27, and that is why the problem has occurred. Okay, so the design of the CPU creates the overflow flag specially for the purpose of informing the programmer that the result of the signed number operation is error. Okay, so now we can understand the role of a V flag. So V flag, we already we talked about the C flag. C flag we talked about when we are considering it as an unsigned numbers, then we check about the C flag. But when we are talking about signed numbers, we must have to check about the V flag. If V flag equals to 0, the error, the result is correct, or V flag equals to 1, there is a problem in an error. So let us see what are the conditions when the V flag is set. Okay, so in 8-bit signed number operations, V is set to 1 if either of the following condition occurs. So there are two conditions, okay, where it is going to set the V flag. So first of condition already we have discussed, that if the carry propagates from D6 to D7, but the carry is not propagating from D7 to C. So this is the first condition, that over here you can see that over here the carry is not propagating into a carry flag, okay, but a carry is propagating from D6 to D7. So this is the one reason, means this is the reason that will be telling you that there is an error. The second is there is a carry from D7 out to carry 1, but there is no carry from D6 to D7. Now this is, in this case, what happens that if the carry is generated from D6 to D7, and if again the carry is generated from D7 to carry, okay, then you will be finding it out that the sign will not get altered. Okay, the resultant sign will not get altered. Means if I am adding two negative numbers, the result must be a negative number. Okay, so if there is a carry generated from D6 to D7, and if a carry is generated from D7 to out, you will be finding it out that 1 plus 1 plus 1, sum is 1, carry is 1. Okay, so the sign of the result is not going to get altered. So this is the reason that if the carry is generated from D7 out to this, but if carry is not generated from D6 to D7, that will also show you that there is an error. If carry is generated from D6 to D7 and carry is generated from D7 to carry, then there will not be any kind of an issue. Okay, so these are the two conditions where you will find it out that V flag would be raised. And raising a V flag, yes, we can understand that, yeah, there is an error in the result. Okay, so the same thing, in another word, the overflow flag is set to 1 if there is a carry from D6 to D7, but there is no carry out. This means that if the carry is from D6 to D7 and D7 to out, V is equals to 0. Already we have discussed this. Now, yeah, we see that the N flag is also going to give you the sign of the result, and S flag is also going to give the sign of the result. Okay, but now in the case of an overflow problem, it may be the case that sign may get altered. Okay, so the correct sign of your result can be reflected by the sign flag. So let us see the point of difference between what is the N flag and V flag. Okay, so in the operation in the sign numbers, okay, all this discussion, it is only applicable for the sign numbers concept. If there is an unsigned number, we need not have to think much about it. Okay, so in the operation of the signed number, the overflow is possible, which corrupt the results and negates the sign bit. Okay, so when there is an overflow, already we have seen in the example that the result is corrupted as well as the sign is altered. Okay, so If we had two positive number in case of overflow, the N flag would be showing 1, the result is negative. But the S flag helps us to know the correct sign of the real result. Okay. So if we check the V flag in addition to D7 bit, if V flag is equals to 0, it shows that overflow has not occurred and sign flag would be the same as the D7. That is the resultant real. But if V flag is equals to 1, then you can say that in that case the overflow has occurred and sign flag would be opposite to that of your D7. Okay, it is exactly opposite to, because it is XORing of your D7 and N flag. Okay, so to show the sign of the real result which is not corrupted. So if V flag is raised, then we need not have to depend upon the N flag for the sign of the result. We need to check our S flag. That is the main thing. Okay, so these are the things that you need to take care about when you are carrying out the sign number arithmetic. So once again, let me revise the same thing once again. So whenever you are dealing with the sign numbers, then there can be a problem of an overflow, and to indicate an overflow problem we are going to have a V flag. So whenever V flag is raised, the sign is not the N flag reflected by, but the sign of a correct result is reflected by the S flag of your ABR. So these are the things. Okay. Now with that, let us discuss some of the logical and the compare instructions that are available in the AVR microcontroller. So apart from IO and arithmetic instructions, there are some logical instructions, and they are very widely used in programming. Okay, so some of the commonly used logical instructions are being listed below. The first instruction is an AND instruction. So this instruction, the syntax is AND RD comma RR, and the result would be stored in your RD. So this instruction will be performing a logical AND on the two operand and place the result into the left operand. So this is as simple as the ending of the two number. Okay, but there is also another instruction, that is ANDI, means immediate value is being ended with your RD register. Okay, this instruction, in which the right hand operand can be constant value, so this k can be a constant value. Okay, now after executing an AND instruction, the Z flag, S flag and N flag, they are going to be reflected, means they are going to be affected by this operation. Already we have discussed that each and every instruction will not be affecting the flags, so we will also be looking into that which are the instructions that are going to affect the flag. So AND instruction, it is going to affect only these three flags, Z, N and S flag. Okay, so N is same as D7, and if the result is equals to 0, Z flag is equals to 1. Okay, the AND instruction is often used to mask the certain bits of an operand. So it is, yeah, we already know that it is used for the masking purpose. Means if I want to mask the upper 4 bits, I'll be masking them, or I'll be performing AND operation with the 0 for that particular 4 bits. Okay, so that is used for the masking purpose. There is OR. So this instruction perform the logical OR on the two operand and place the result into the left hand side operand. Means RD is OR with RR and the result is placed into RD. And same as was the case with your AND instruction, there is an ORI instruction which can immediately, it can OR the register value with any immediate value or a constant value which is being represented by k, and again it is supposed to be affecting your Z flag, S flag and N flag, and N is D7 and Z is equals to 1 if result is equals to 0. But for what purposes we generally use an OR instruction? The OR instruction can be used to set certain bit to 1. Okay, when we want to make some bit to 1, we will use the OR operation. If you want to mask the bits, then we will be using an AND operation. The other is an Xor operation. Okay, so it is performing a logical Xor operation on the two operand and place the result into the left hand side operand. Again, it is going to reflect Z flag, S flag and N flag. Okay, so for what purpose generally we use XORing operation? So XORing operation is generally used to see that two registers are having the same value or not, because we know that if as XOR, if two values are same, the result is 0. Okay, so yeah, we can check the Z to 0 flag and perform the XOR operation. Okay, to see that whether two values in the the registers, two registers are having the same value within it or not. Okay, another widely used application of XOR is to toggle the bits of an operand. So that we will be looking into in many of the program, that if we want to toggle the bits, then also we will be using an XOR operation. The another is com instruction and another is nag instruction. Okay, so this com instruction complement the content of a register, but we need to see that the complement is ones complement. Okay, so the complement actions change all the zeros to 1 and all the ones to 0, and it is also called as a ones complement. So already we know that what a ones complement. So if you want to make a ones complement of a number, then you can use COM. Okay, but there is another instruction, that is what we called it as an NEG instruction, that is negate instruction. So this instructions take the twos complement of a register, means whatever the value you have taken into. So yeah, that is generally being used when we use the sign arithmetics. Okay, so we know that if the result is negative, if we check a sign flag, and if sign flag shows that the result is negative, we need to take a twos complement of a number, and that can be done with the help of an NEG instruction. You can use COM, but you need to add one to it. So rather than wasting to one machine cycle extra, we can have an instruction that it can be executed in one machine cycle, that is an NEG, and that will take the twos complement of a number. And the last is a compare instruction. So already we already discussed a compare instruction in CMP instruction in 8085 microprocessor. Same way we are having a compare instruction in our AVR microcontroller, that is CP, CPRD comma RR. Okay, so this AVR has a CP instruction for the compare operation. It is merely a subtraction, means it will be doing RD minus RR, and if flag is raised, RD is less than RR. If flag is not raised, RD is less than RR, and if zero flag is raised, RD is equals to RR. This is very simple concept that can be used. Okay, so compare instruction is really already a subtraction instruction that already we have seen in our case of 8085 microprocessor. So it is a replica of it. Okay, the only difference is mnemonics. In that case it is CMP, over here it is only CP. Okay. You can also compare the immediate value. So we were having CPI in our 8085. Same way we are also having CPI instruction in our AVR microcontroller also, that will compare the immediate value, any constant value, with any register. Okay, but in case of our 8085, it was only the accumulator which can be done a comparison. But in case of this AVR, any 32 general purpose register can be used for the comparison, as well as the comparison with the constant value. Okay, so this is all from my side for today. If you are having any kind of query, doubt, you can ask me. Any query,
No doubt,
friends?
sir.
No doubt. Okay, so in the next. Okay, so in the next class we will be talking some of the another function of our AVR microcontroller. So that is all from my side. Thank you everyone.